Transpose of a scalar multiple. Hello everyone. To begin today's lesson, let's first quickly recap what we have already covered. In our previous sections, we learned the fundamental process of finding the transpose of a matrix, which simply involves interchanging its rows and columns. Now that we are comfortable with that basic operation, we will move forward to explore how the transpose operation interacts with a scalar. Before we dive into the specific properties, let's ensure we are clear on the terminology. A scalar is simply a real number. When we talk about scalar multiplication in matrices, it means we take this single number and multiply it by every individual element within the matrix. Understanding this will be crucial as we move into the mathematical properties in the next few slides. Understanding the concept. The property of the transpose of a scalar multiple tells us something very convenient. The order in which we perform these two operations does not change the final result. Specifically, if you multiply a matrix by a constant scalar and then take the transpose of that result, you will get the exact same matrix as if you had first taken the transpose of the original matrix and then multiplied it by that constant. To express this in formal mathematical notation, for any matrix A and any scalar k, the transpose of k times is equal to k times the transpose of A. To ensure we are all on the same page with the symbols used here, the letter k represents our scalar, which is simply a constant number. The letter A represents our matrix. A' denotes the transpose of matrix A, and finally, k denotes the scalar multiplication of matrix A by the constant k. Now that we have a basic understanding of what a transpose is and what a scalar represents, let's dive into how these two concepts interact. In the next slide, we will break this property down step by step to see exactly why this logic holds true. Step-by-step breakdown of the property. Now that we have introduced the formal notation, let us dive deeper into why this property actually works. To make this clear, we can visualize the process as two different paths that lead to the same final result. First, let us examine path 1, which represents the transpose of k times A in this sequence. We start by multiplying every single element within matrix A by our scalar. Once we have obtained this resulting matrix, we then perform the transpose operation by interchanging its rows and columns. Now, let us consider path 2, which is k times the transpose of A in this case. We reverse the order of operations. We first interchange the rows and columns of matrix to find the transpose of matrix A. After that, we multiply every element of this transposed matrix by the scalar k. You might wonder why these two different approaches yield the same answer. The reason is that the scalar k is applied to every single element in the matrix, regardless of its position. Because the multiplication affects every element uniformly, the final values in the matrix will be identical, whether the transposition happened before or after the multiplication. To see this logic in action with actual numbers, let us move forward to the next slide and work through a concrete example. Illustrative example. Now that we have discussed the theoretical property and the two different paths of operation, let us verify this concept with a concrete example to see it in action. First, let us look at the values we are given. We have a matrix A, which is a 3x2 matrix. Its first row contains 2 and -1, the second row contains 4 and 0, and the third row contains 3 and 5. We are also given a scalar, k, which is equal to 3. We will begin by calculating the left-hand side of our property, which is the transpose of k times A. In the first part of this process, we find the scalar multiple, k times A. To do this, we multiply every single element inside matrix A by 3. This results in a new matrix where the first row is 6 and -3, the second row is 12 and 0, and the third row is 9 and 15. Next, we find the transpose of this resulting matrix. By interchanging the rows and columns, our 3x2 matrix becomes a 2x3 matrix. The first row is now 6, 12, and 9, and the second row is -3, 0, and 15. Now, let us calculate the right-hand side of the property, which is k times the transpose of A. In this path, we start by finding the transpose of matrix A first. By switching the rows and columns of the original matrix, we get a 2x3 matrix where the first row is 2, 4, and 3, and the second row is -1, 0, and 5. Now we multiply this transposed matrix by our scalar, k, which is 3. Multiplying each element by 3, we arrive at a matrix where the first row is 6, 12, and 9, and the second row is -3, 0, and 15. To conclude, let us compare the results from both steps. You will observe that the final matrix from the left-hand side is exactly the same as the final matrix from the right-hand side. Both result in a matrix with the first row as 6, 12, 9, and the second row as -3, 0, 15. This successfully demonstrates that the transpose of k times A is equal to k times the transpose of A. Real-world analogy. Now that we have verified the property mathematically with a concrete example, let's look at a real-world analogy to help you visualize why this logic holds true. Imagine you have a data table that lists the prices of 2 different products across 3 different cities. First, let's consider the concept of scalar multiplication. Suppose there is a sudden 10% tax increase across all these cities. To update your prices, you would multiply every single value in your table by 1.1. Next, consider the transpose operation. Imagine you decide to change the layout of your report for better readability, switching the cities from rows to columns and the products from columns to rows. The key takeaway here is that whether you apply the tax increase first and then rearrange the table, or rearrange the table first and then apply the tax increase, the final price for each product in each city remains exactly the same. This is a practical illustration of the property we just discussed, that the transpose of a scalar multiple is equal to the scalar multiple of the transpose. Understanding this intuition will be very helpful as we move forward to discuss some common mistakes to avoid in the next slide. Common mistakes to avoid. Now that we have verified the property with an example and looked at a real-world analogy, let us discuss some common pitfalls to ensure you avoid these mistakes in your assignments and exams. First, be careful not to confuse scalar multiplication with matrix multiplication. In this lesson, we are dealing with k times A, where k is just a single constant number. As we have already established, the order of operations here is flexible. The transpose of k times A is simply k times the transpose of A. However, please keep in mind that when you multiply 2 matrices together, such as a times B, the rule is different. The transpose of a times B actually reverses the order, becoming the transpose of B times the transpose of A. It is a common slip-up, so be mindful of whether you are working with a single number or another matrix. Second, watch out for partial multiplication. When you multiply a matrix by a scalar, remember that the scalar must be applied to every single element within the matrix. A frequent error I see is students multiplying only the first row or the first column and forgetting the rest. To get the correct result, ensure that every entry in the matrix is multiplied by the constant. Finally, let us address notation confusion. In this context, the prime symbol, the small tick mark next to the A, strictly refers to the transpose, which is the process of interchanging rows and columns. Depending on your other mathematics courses, you might see a prime symbol used to denote a derivative in calculus or as a power in other areas, but here, it refers exclusively to the transpose operation. Keeping these 3 points in mind will help you maintain accuracy in your calculations. Now, let us move to the final slide to summarize our key takeaways. Key takeaways. First, the property that the transpose of k times A equals k times the transpose of A indicates that scalar multiplication and transposition are commutative operations. In simpler terms, as we demonstrated in our step-by-step example and the real-world analogy, the order in which you perform these 2 operations does not change the final result. Secondly, notice that the scalar k remains completely unchanged. We do not apply the transpose operation to k because it is a single real number, not a matrix. Since it has no rows or columns to interchange, it stays exactly as it is. Finally, this property is incredibly useful for simplifying matrix algebra. It allows us to move constants outside of the transpose operation, which often makes our calculations more efficient and much easier to manage. To wrap everything up, let's review the key takeaways from this lesson.